In this video, we will be solving question number 6 to 11 of exercise 1.1 chapter 1 number system. Before we solve the question, let me just give you a review of what we have discussed in the previous video. We discussed about Euclids division lemma, where it said that if there are any two integers such that a is greater than b, then there will exist q and r, where q stands for quotient, r stands for remainder, and the remainder should be greater than or equal to r, but it should be less than the divisor. Makes sense? And we also discussed about Euclid's division algorithm, where it said that whenever we divide any bigger number by smaller integer, let me rephrase that, whenever we divide any bigger integer by the smaller integer, the last divisor will be our HCF. And we talk about how to express integer in the general form. Whenever we want to express any consecutive integer, this is the general form: n plus 1, n plus 2. Example 1, 2, 3, 4. Or we can also start from 99, 100, 101. These are all consecutive integer. Whenever we're talking about consecutive integer, this is the general form. And whenever we want to express consecutive even integer, then we will use 2n, 2n plus 2, 2n plus 4. And for odd consecutive integer, 2n plus 1, 2n plus 3, 2n plus 5. Now let's move on to question number 6. Question number 6 says, show that the square of an odd integer is of the form 8k plus 1. The question says square. And also it mentioned, and that means we're talking about one number, odd integer. So here we will be discussing about square, and we will be discussing about one integer, which is odd. So that means we'll be talking about one odd integer, but that one odd integer can be any odd integer. So if we consider a as our odd integer, then we have to solve for a square, that is the square of our odd integer, and we have to show that this can be expressed in the form of 8k plus 1. So like I said in the previous slide, I've shown you how to express odd integer 2n plus 1. We usually use this form, general form, and if we want to square it, then let's use the algebraic identity: a square plus twice ab plus b square. So using this identity, I can express this as 4n square plus 4n plus 1. I have 4n common in this two term. 4n n plus 1 plus 1. So if we see this general form, does it look familiar to our first general form, that is for consecutive integer? n plus 1 is a general form for two consecutive integer. And let me show you with example. Let's say our two consecutive integer is 1 and 2, or 6 and 7, 8 and 9, 10 and 11, 99 and 100. Okay, let's look at the 5 example. See, here 2 is even, here 6 is even, 8 is even, 10 is even, 100 is even. So we can conclude that among any consecutive integer, at least one of them is even. So if we want to express that, then we can express this n plus 1 as 2k. This means that at least one, since at least one of them is even, it can be expressed as 2k. Now let me show you the proper answer for question number 6. I have written here, let the given odd integer be a, then a is equal to 2n plus 1. Since a is odd, I have taken the square, expand with the help of identity, and this is what I got after I take 4n as common, and this is our general form for two consecutive integer. And I have also given the explanation here. Since n plus 1 are consecutive integer, one of them must be even. Therefore, their product n plus 1 is even. Fair enough. Therefore, n plus 1 can be expressed as 2k, where k is any integer. Now, substituting the value of n plus 1 for a square, we get 4 2k. So in place of 2k, we had n plus 1. We have substituted 2k here. So it's 4 2k plus 1. 4 2k plus 1. And if I open the bracket, then I will get 8k plus 1. Hence, the square of any odd integer is always of the form 8k plus 1. It is very important to give conclusion for the question once you are done with the answer. Question number 7. If a is divisible by neither 2 nor 3, show that a square minus 1 is divisible by 24. Okay, over here the question says it is not divisible by 2 and it is not divisible by 3. Now think about it. If a number, if an integer is not divisible by 2, what does that mean? It is not divisible by 2, then we can say that the number is not even. This is not even, because had it been an even number, then it would definitely have been divisible by 2. So if it is not even, then we can conclude that this number is an odd number. Now, an odd number means the general form will be 2n plus 1. This is one thing that we need to keep in mind. The second thing is, it says it is not divisible by 3 either. So what does that mean? So let me take some odd number: 1, 3, 5, 7, 9, 11. So if it is not divisible by 3, then this is not the number, because 3 is divisible by 3. This is also not the number. So let us divide 5 by 3. 1 3, our remainder is 2. We cannot take 1 because Euclids division lemma say that whenever we are talking about two integer a and b, the greater number should be the dividend. This was one of the condition, that the dividend must be greater than the divisor. But here we are talking about divisible by, so that means 3 is acting as a divisor and 1 is lesser than 3, so 1 cannot be the dividend here, so this also fails to be considered as the number that we're looking for. Okay, 5. Okay, so we have divide 5 by 3. Our remainder is 2. When we divide 7 by 3, our remainder is 1. And okay, and Euclid's division lemma also says that the remainder should be greater than or equal to 0, but it should be less than the divisor. So our divisor here is 3, so the remainder, the possible value of remainder is 1 and 2 only. It cannot be 3 because it has to be less than 3. So 1 and 2 they are the possible values of r. It cannot be 0 because if it is 0, then that means the dividend is divisible by 3, but the question says it is not divisible by 3, so the remainder being 0 is ruled out. So our possible values of 1 and value of remainder is 1 and 2. Okay, so things to remember while solving this question is our a is an odd number, and since it is an odd number, the general form is 2n plus 1, and our possible value of remainder is 1 and 2. So how can we express this in general form for the remainder? So if it had been divisible by 3, then the expression that we can use is 3n, or let's say 3a. Then if the remainder is 1, then we can use plus 1. And for the remainder 2, we can write the general form as 3k plus 2. So these are the things that you need to know before solving this question. And in the next slide, I have explained and written the proper answer. Let us go through the answer now. Question number 7. Since a is not divisible by 2, it must be odd. And since a is not divisible by, I've written that twice. And since a is not divisible by 3, it leaves remainder 1 or 2 when divided by 3, because a is equal to 3q plus r. Here 3 is our divisor, q our quotient, and r our remainder. And our remainder is greater than 0 since it is not divisible by 3, and it is less than 3 because our divisor is 3. Now two case arises when it leaves remainder 1. Our a can be expressed as 3q plus 1, because 3q is divisible by 3. That means remainder is 0, but if we add plus 1, then our remainder becomes 1. So we want to show that a square minus 1 is divisible by 24. So if we can show that this expression a square minus 1 is divisible by 8 and 3, then we can conclude that the expression is divisible by 24. Okay, let me show you here. Now we are concerned about is a square minus 1. Here I have substituted the value of 3q plus 1 over here, and there was square over here, so I've written the square here. Minus 1 comes from here, minus 1, and I have expanded this term using identity a plus b whole square. This is what I got after cancelling out minus 1 plus 1. I am just left with these two terms, and I can take 3 common, then I'll be left with this. So there is 3. The expression has 3 outside the bracket, and inside the bracket 3q squared plus 2q. What we are interested is not the terms that is inside the bracket, but the coefficient that is outside the bracket, which is 3. So if there is coefficient outside the bracket and there is no term after this, then we can say that this is divisible by 3. So hence a square minus 1 is divisible by 3. We can safely say that. Now I also told you that since a is odd, it can be expressed as 2n plus 1. Let us use this in the next step. A is equal to 2n plus 1, and then let us try to substitute this value in the expression a square minus 1. So a square, this is our a square minus 1. I have used the identity to expand this term, minus 1. The rest is the result of the expansion of our algebraic identity a plus b whole square. I can cancel this, then I'll be left with 4n plus 1, right? And then we know that n plus 1 of the number is even, and n plus 1 is the general form for consecutive integer, and one of them is even, so we can express these as 2k. Then we have 4 2k, that will give us 8k, and 8k can be divided by 8. So for the first case, when the remainder is 1, it can be divided by 3. That's the first thing. Second, it can be divided by 8. Therefore, a square minus 1 is divisible by both 8 and 3. That means it is divisible by 24. 8 times 3 is 24. Now let's talk about when the remainder is 2. So for the remainder 2, we can express our term a as 3q plus 2. 3q when it is exactly divisible by 3, plus 2 when the remainder is 2. If it is exactly divisible by 3, then our remainder will be 0 plus 2. Our remainder is 2. We're talking about when the remainder is 2. Then a square minus 1, substituting the value of a over here, a square minus 1 minus 1. Expanding the term, 9q squared plus 12q plus 4 minus 1. This I'll get 3. So 9q squared plus 12q plus 3. I can take 3 common. Then we don't care about what is inside the bracket as long as there is no there's no number after this term, like 1 or 2. We do not care about what is inside the bracket, we just care about what is outside the bracket. So it is 3, so that means this is divisible by 3. This is divisible by 3. Just add that. This is divisible by 3. And again, a squared minus 1 is divisible by, this is divisible by 8 as well, because we have shown in case number 1 that a is odd. So you can see from here the same will follows. And as shown earlier, since a is odd, a squared minus 1 is also divisible by 8. Hence a squared minus 1 is divisible by 8 times 3 is equal to 24. Give the conclusion. Therefore, if a is divisible by neither 2 nor 3, then a squared minus 1 is divisible by 24. I hope you understand question number 7. Let's continue with question number 8. Show that any square number cannot be put in the form 4k plus 2. Okay, it said any number. So any number, this can be odd, this can be even. So when n is even, then we'll be talking about 2n squared. When n is odd, then we'll be talking about 2n plus 1 whole square. And we have to show that the result of both these cannot be expressed in the form of 4k plus 2. So 2n squared will give us 4n squared. It doesn't give us 4k plus 2. And if we expand these, then we'll get 2n whole square plus twice 2n 1 plus 1 whole square is equal to 4n square plus 4n plus 1. We can take 4n common, n plus 1 plus 1. These we can write it as 2k plus 1. So it will give us 8k plus 1. After expanding these, we are getting 8k plus 1, which is not 4k plus 2. So hence we have shown that any square number cannot be put in the form of 4k plus 2. Let a be any integer. If a is even, two cases arises. The first is if a is even, a can be expressed in the general form 2n, then a squared 4n square, and this is our case number 2. If a is odd, then a is equal to 2n plus 1, a square is equal to 2n plus 1 whole square, 8k plus 1. We have shown that any square number cannot be put in the form of 4k plus 1. 4k plus 2. Now let us solve question number 9. Question number 9 says, show that any square number is of the form 3n or 3n plus 1. We have to show that any square number can be written in the form of 3n or 3n plus 1. And if we want to express in the form 3n or 3n plus 1, then we know that the number should be divided by 3. And according to Euclids division lemma, when the divisor is 3, then the remainder should be less than 3. So it can be 0, it can be 1, or it can be 3. So 3 case arises, that is when the remainder is 0, then our number will be, let's say, 3 cube, in the form of 3 cube. And when the remainder is 1, then our number is 3 cube plus 1. If our remainder is 2, then our number is 3 cube plus 2. And we have to square each of these number, and then we will have to see if we can express this 3 number in the form, either in the form of 3n or in the form of 3n plus 1. Let us look that in the next slide. So by Euclid's division lemma, take any integer a and divide by 3. Why divide by 3? Because we want to express them in the form of 3n or 3n plus 1. So a must be one of 3 cube when the remainder was 0, 3 cube plus 1 when the remainder was 1, and when the remainder was 2, the number 3 cube plus 2. If so, this is case number 1. If a is equal to 3q, then a square. Where does this a square comes from? This comes from the question, show that the square number. So we have taken that number integer pa, so we have to find a square. If a is equal to 3q, we have to find a square is equal to 3q whole square is equal to 9q square. We can take 3 common, and then inside the bracket 3q square. Outside the bracket there is number 3, so that means this is divisible by 3. So this can be expressed, we can express this in the form of 3n. We then consider that. So this has been expressed as 3n. Let us move on to case number 2. If a is equal to 3q plus 1, this is when the remainder is 1, 3q plus 1. So a square is equal to 3q plus 1 whole square, expanding the identity 9q square plus 6q plus 1. Then we cannot do about this. We can leave plus 1 as it is, because in the question it says plus 1. So let's not disturb this term plus 1, and for this 2 term we can take 3 as common, and we can just express this as n, 3n plus 1. So for the second case, when the remainder is 1, we have expressed the number, the integer, the square of the integer in the form of 3n plus 1. Moving on to case number 3, that is when the remainder is 2, that is 3q plus 2. A square is equal to this. When we expand we will get this expression 9q square plus 12q plus 4. Now this 4 is a bit problematic because we cannot take 3 common out of 4, and then in the question either we have to express the square of the number either in the form of 3n or either in the form of 3n plus 1. There is no 4 mentioned, so what we can do is we can just modify and write 4 as 3 plus 1. We can modify this, and I have done that. 3 plus 1, then we can give this plus 1 as it is, and from this 3 term we can take 3 common. Now this has been expressed in the form of 3. We can consider this as n, so 3n plus 1. So for all the 3 cases we have expressed it in the form of 3n, and for the remaining 2 cases we have expressed the square of the number in the form of 3n plus 1, and yeah, for this also 3n plus 1. Therefore every perfect square is either divisible by 3n or 3n plus 1. That concludes question number 9. Let us continue with question number 10. Show that one of 3 consecutive odd integer is a multiple of 3. One of, so 3 consecutive odd integer. That means we have to use this general form, 2n plus 5, and we have to show that out of these 3 consecutive odd integer, at least one of them is a multiple of 3. We have to show that. Now if we divide any number by 3, that is if 3 is the divisor, then the possible values of our remainder is 0, 1 and 2. That is what our Euclids division lemma says. Now again we'll be discussing 3 cases for this question number 10. So first we'll discuss when 0 is the remainder, when 1 is the remainder, and when 2 is our remainder. When 0 is the remainder, then we can express these as 3k, 3k plus 1, 3k plus 2. In the previous question I have used the expression 3q plus 1, 3q plus 1. It's the same. For this question I'm using k so that you will know that q or k is not the absolute expression, but we can alter them. We can use both of them. 3k plus 1, 3k plus 2. This will be our 3 cases, and then we'll have to discuss for this separate consecutive integer. Let's see how it goes. Let the 3 consecutive odd integers be 2n plus 1, 2n plus 3, 2n plus 5. When we divide n by 3, the possible remainders follow 0, 1, 2. You can write at the side by Euclids division lemma. This number 1, when n has remainder 0, we can write n is equal to 3k for some integer k. Now our first odd integer is 2n plus 1. So since here n is remainder, for the first case we're considering for when n has remainder 0, so the expression is 3k. It will just be 3 6k plus 1. So it is 6k plus 1. Moving on to second odd integer, 2n plus 3. Substituting the value, n is equal to 3k. 2 into 3k, 6k plus 3. We can take 3 common. Then we can say that this is a multiple of 3. For the third odd integer, 2n plus 5, this is the general form. Substituting the value of n, we get 6k plus 1. So for this is the first case number 1, when n has 0 as remainder, that is n when n is of the form of 3q or 3k. We can see that out of the 3 consecutive odd integer, this second odd integer is a multiple of 3. Why? Because we are able to express this in the form of 3. But for this case, it is 6k plus 1. So although we can write 6k in the form of 3 to k, there is plus 1 after this term, so that means remainder is 1. Whenever the remainder is not 0, that means it is not a multiple of 3. So for our first case, this is not a multiple of 3, but this is a multiple of 3, 2n plus 3. And for the third odd integer, 2n plus 5, we get 6k plus 5. Again, even though if we can express 6k as 3 to k, there is plus 5 after that term, so remainder is 5 here. So we cannot say that this is a multiple of 3, but at least from our case number 1, we can see that at least 1 is a multiple of 3. And what does our question say? Show that 1 of 3, we just have to prove for 1. It can be either these 2n plus 1, or it can be 2n plus 3, or it can be 2n plus 5. We just completed case number 1 when the remainder is 0. Now let's move on to case number 2, that is when the remainder is 1. Case number 2, when n has a remainder of 1, then n can be expressed as 3k plus 1. First odd integer 2n plus 1, in place of n, let us substitute this value. So 2n, 3k plus 1 plus 1 over here plus 1. Expanding this, 6k plus 2 plus 1 is equal to 6k plus 3. We can take 3 common here. So this is 3, and that means this is a multiple of 3. Checking for the second odd integer, we get 6k plus 5. This is not a multiple of 3. For the third odd integer, we get 6k plus 7. This is not a multiple of 3. So for the second case, 2n plus 1, this is a multiple of 3. Now let's move on to when the remainder is 2. That is 3k plus 2. When n has remainder 2, n is equal to 3k plus 2. Our first odd integer, substituting the value of, okay, you can first express the general form over here, 2n plus 1. So in place of n, I have substitute the value n is equal to 3k plus 2. Expanding them, I get 6k plus 5. This is not a multiple of 3. Second odd integer, I have substituted the value of n, 6k plus 7, no, not a multiple of 3. Third odd integer, 2n plus 5. 6k plus 9, I can take 3 as common. When I took 3 as common, then it gives me 3, 2k plus 3. Yes, this is in the form of 3, and that means this is a multiple of 3. So in our first case, that is when n has remainder 0, our first odd integer was not a multiple of 3 because of this. Our second odd integer, we were able to express that in this form, so yes. For third odd integer, 6k plus 1, no, at least one of them is a multiple of 3. That for this case, the condition has been satisfied. Moving on to second case, yes, no, no. So for the second case, at least one of them is multiple of 3. Again, the condition satisfied. Moving on to case number 3, no, no, yes. So we are able to express for all the 3 cases that whenever whenever the number is divided by 3, we have 3 possible values of remainder, that is 0, 1 and 2. And since we are talking about 3 consecutive odd integer, we have taken the general form 2n plus 1, 2n plus 3 and 2n plus 5, and we were able to prove that one of the 3 consecutive odd integer is a multiple of 3. Give your conclusion, and we are done with question number 10. Now coming to our last question, question number 11. Show that the product of any 3 consecutive even integer is divisible by 48. So here we are talking about consecutive even integer. That means we will be using this general form. And we are talking about product. That means we will be multiplying these 3 terms. So 2n plus 2, 2n plus 4. We will have to multiply this, and then we have to show that the result of this can be expressed in the form of 48. So we have to express this as 48 something. Whatever number or whatever terms or expression can come here, but it should not be followed by plus 1 plus 2, just 48 and something, not bound by other operation as such as addition, subtraction. The only operation that should be associated with 48 is multiplication. We have to show that, and our work will be done. Okay, so let us try to express this. Let us take 2 common from here, then we'll be left with n plus 1, and from here let us again take 2 as common, then we'll be left with 2 n plus 2. Let us group 2, 2, 2, we'll get 8 because 2 times 2 times 2 is 8. Then we're left with n plus 1 and n plus 2. Now 8, this is a constant, we don't have to do anything about 8, but when we look at this general form, this is a general form for 3 consecutive integer, and I believe that in the previous video we have come across one such question. We have discussed about one such question dealing with 3 consecutive integer, and I have also supported the answer by giving suitable example. I'll be giving the examples here again So let's see. N plus 1, n plus 2. This is talking about any three consecutive integer. I'll take 1, 2, 3 over here, and 7, 8, 9, any three consecutive integer. Whatever number you start with, just begin with that number without skipping any number. 99, 100, and 101. So one such property for three consecutive integer is that one of the number is even. Let's see, here 2 is even, here 8 is even, here 100 is even. Take any three such consecutive integer: 200, 201, 202, 200, 201, 202. It is even, it is even. So the property says that at least one of them must be even. So that means this number can be expressed in the form of 2k, because at least one of them is even. And the second property for three consecutive integer is that at least one of them is a multiple of 3. Let's check for that one. 3, and here 9, and here 99. And for any three consecutive integer, you will always find that at least one of them is a multiple of 3. So we can express that in the form of 3. So if we multiply 3, and we can express it in the form of 3, and so this is 6, and I have 8 over here. 8 times 6 is 48. That is how we will prove this question number 11. Let us look at the proper answer. Let the three consecutive even integer be 2n, 2n plus 2, 2n plus 4. Product, I've taken 2 common, 2 common. We're left with this expression. But n plus 1 is an expression of any three consecutive integer. Among n plus 1 and plus 2, exactly 1 is a multiple of 3. Therefore, one of them is divisible by 3. And among n plus 1 and plus 2, 1 is even, hence is a factor of 2. Therefore, n plus 1 is divisible by 2 times 3 is equal to 6. Hence, if this is divisible by 6, then this whole expression is divisible by 48, because I already have 8 here, and we know that 8 times 6 is equal to 48. That is how we will conclude question number 11. So this is the end for exercise 1.1. In the next video, we will continue with exercise 1.2. And if at all, if this video is helping you to understand the concept better, then please do consider subscribing to my channel. Please give me a like, and give this video a like, and comment, and please share this video. We will meet again in the next video. Thank you so much for watching.